All right, guys, let's go ahead and get started. So, welcome to today's webinar. Today, we are going to be talking about the Fluid Dynamics Engineer role on the 3D Experience platform. For those of you who don't know me, my name is Steven Zalis. I'm the Simulation Product Manager here at CADimensions. So, anything that is simulation related, whether it be structural simulation, flow simulation, plastics injection, desktop products, platform products, anything you can think of is going to run through me. So I'm going to be putting on this webinar for you guys today. We are going to run through a brief overview of the Fluid Dynamics Engineer role on the platform, talk a little bit about what it does really well, compare it to desktop, and then there's going to be time for questions at the end. So if you guys do have questions that come up, feel free to throw them in the chat and we can get to them towards the end of the presentation. So let me go ahead, turn my camera off so you guys can see full screen, and we'll dive right into it. And we're going to talk a little bit about what 3D Experience simulation is as a whole. And what it really is it's a merger between a couple of different products under the Dassault System brand. The product that we're all very familiar with is SolidWorks, right? SolidWorks is a desktop CAD product that allows us to do a lot of different things. And over the years, they've developed a lot of really nice simulation add-ins for SolidWorks, like structural simulation, SolidWorks flow simulation, SolidWorks plastics, right? All of these really nice tools that have been built into SolidWorks that we can leverage that technology and get design answers faster. The 3D experience portion of it actually brings in another brand under the Dassault System umbrella, which is Abacus, right? And Simulia. It allows us to leverage the world-class Abacus solvers and throw everything under one roof, right? So we can go ahead and design in SolidWorks. That's our kind of bread and butter. That's what we're familiar with. We can go ahead and use various different methods to bring our geometry into the 3D Experience platform and then pull that geometry out of the 3D Experience platform into some of our other analysis apps, like specifically in this case, Fluid Dynamics Engineer. We have Structural Mechanics Engineer, Plastics Injection Engineer. We've touched on all of these previously in a couple of other webinars I've done, but what it really is a fully integrated simulation solution with both PLM, which is product lifecycle management, revision control, lifecycle documentation, things like that, and our CAD systems. So we can go ahead and push and pull our geometry to and from SolidWorks to allow us to make our changes, update our geometry, and go from there. We have simplified applications with tools specific for each simulation domain. Now, desktop does this really well too, right? We have our structural simulation package, we have our flow simulation package, plastics injection package. We have all of these kind of siloed out, and the 3D Experience platform is no different, right? In this case, we are dealing with our fluid flow solution. So we are dealing with what's called a role or an application for Fluid Dynamics Engineer. And it's fully integrated with our 3D Experience platform, meaning we have really, really easy collaboration, especially in these times. It's really difficult, or it can be very difficult, to manage large simulation data sets, right? Results files, making sure we have the right revision of the file, everything's up to date. We do that very quickly with the 3D Experience platform. You can access your geometry from anywhere and get our results faster than ever. This PowerPoint, and really every 3D Experience simulation PowerPoint that or presentation I'm going to deliver this year, has 3 key points, right? Obviously, we're dealing with the simulation domain on the platform. So our first key point is always going to be to analyze. We always want to be answering the question, what are we looking for, right? Whether it's flow rates, pressure drops, we want to maintain the fact that our electronics are cool enough, whatever we're looking for, we want to make sure that the analysis is done correctly. Then secondarily to that, we want to collaborate, right? We need to share these results with somebody. Normally, we're not working on an isolated unit, right? We're working with multidisciplinary teams. We're working with stakeholders. We're working with vendors. We need to be able to share that information just as easily as we created the analysis case. And from there, kind of more of the housekeeping back-end type stuff, we need to be able to manage that data very quickly, right? Things like revision control, lifecycle management. We need to make sure that we have the correct version of the file going to the correct people so we can go from there. So those are the 3 key points that are not necessarily specific to the simulation domain on the 3D Experience platform. The collaborate and manage data is really any file we're working with, whether it's a PDF file, a CAD file, an Excel document, whatever it might be. We always want to be able to collaborate and manage that data. The analyze portion is a little bit more specific to the products that I cover, but we always want to make sure whether we're running an analysis in desktop or the new 3D Experience tools that we're getting the correct analysis the first time. So where the 3D Experience platform shines is exactly those three key points. So this is just a quick example overview of what we get in terms of the Fluid Dynamics Engineer. And it starts with our lifecycle management app. This is a motorcycle assembly. It allows us to pick and choose which sub-assemblies we're actually analyzing. In this case, we're just taking a look at all the different components. And we are going to be analyzing specifically the exhaust bracket down on the lower left there. And we're going to be taking a look at the one that has the simulation data attached. So in our lifecycle management tools, we can go ahead and grab all of that information very, very quickly. So from here, we're interested in this exhaust. Because this is integrated so tightly with our PLM system, we can grab that revision, start up our analysis case, and go very quickly through this, right? We're going to go ahead and use the guided assistant. I'll talk about this a little bit more in depth later, but we can go and run through and extract our flow domain very, very quickly. We can throw some lids on it because this is an internal analysis. We can apply our material properties. We can pick, in this case, a porous media. We're looking at the catalytic converter in the outlet here. We can go ahead and specify what type of physics we want, whether it's a transient step, a steady state step, specify our boundary conditions, different zones, right? Whether we have heat sources or things like that. In this case, we're specifying the properties of our porous media. We can go ahead and create our mesh very, very quickly, which in this case is one of my favorite features of the Fluid Dynamics role. We can go ahead and solve our analysis and take a look at our flow and thermal performance in this case. We want to look at velocity vectors, pressure drops, whatever we want to look for. We can get all of that data very, very quickly. Because this is so tightly embedded in the PLM software, we can go ahead and update our geometry very quickly, update our simulation, and all we have to do is remesh. In this case, we're going to create a new revision or replace by a revision. So we're replacing revision A with revision B. And all we need to do is replace in the lifecycle management app, rerun our simulation. Everything we can see in our assistant, everything is green. So all we need to do is rerun. Very similar to how desktop works, right? We can go ahead and create a new configuration. We can make our changes, and we can go ahead and compare our revisions side by side, right? We have revision A, revision B. We can solve in the cloud if we want to, take advantage of the cloud solution. We can go from there, get our results even faster. So it is a really, really tightly embedded tool, and I really enjoy using this tool because it allows us to get our design insights much, much faster than we would if we had to kind of do all this stuff by hand or build physical prototypes or anything like that. So the advantage of virtual simulation is, just tenfold over anything that we can do by hand. And on the 3D Experience platform, it's even more so because everything, we consider it a single source of truth, right? You're all pulling from the same data. So that exhaust that we're analyzing is the same one that we created in the design phase, is the same one that's embedded in our revision cycle. Everything is tied together. So that's what makes everything really, really exciting. In terms of what we just saw, this is not exactly the same example, but this is a typical workflow in the 3D Experience platform, whether we're dealing with structural simulation, flow simulation, anything like that, right? The first thing we need to do is start with our geometry. And we can do a couple of different things. We know what our inputs are going to be, right? Our coolant passages. We know our operating mode, whether it's steady state or transient. We know the coolant properties. In this case, in this analysis, it's just water. But if we had a refrigerant or a specific coolant, we can go ahead and upload that in the database. We know what our climate conditions are going to be. We know what our ambient temperature and pressure are going to be. From here, we're just kind of following the chain, right? The model preparation, obviously we need to idealize our geometry, defeature anything that's not super important, like cosmetic fillets, extruded text, things that are going to be difficult to mesh or that are going to jack up our mesh count way more than we need it to be. We're going to go ahead and specify our computational domain and our fluid flow regions. We're going to set up things like our fluid and solid materials, right? We know in this case that engine jacket is going to be some kind of metal. We know that our fluid in this case is going to be water. We can specify our operating scenario, right? So step 2, we can define our fluid and solid physics. So we can specify laminar flow, turbulent flow, a mix of both. We know whether or not we want to include thermal contacts like heat transfer, our fluid structure interaction, FSI. We can go ahead and specify our advanced solver controls if we wanted to get really granular with it. We know what our initial or boundary conditions are going to be, whether or not we're doing a transient study or a steady state study. Basically, this would run us through the wizard in desktop, right? We can check on things like internal or external flow. We can check on time dependency, gravity, heat transfer, right? We can choose whether or not we're going to consider the energy equation. We can go from there. That's basically what this step 2 is, right? So step 1, we go ahead and prep our model, be it in the 3D Experience platform or inside of SolidWorks. That step remains the same. The operating scenario would be basically our wizard from desktop flow. Step 3, automatic meshing. I really like this step. The mesher in the 3D Experience platform in Fluid Dynamics Engineer, in my opinion, is what really sets it apart from desktop, because it does a couple different things, right? The first one is the automatic fluid volume extraction, which desktop does do, but it takes a specific step, right? When we run the check geometry tool on the desktop program, it does a Boolean extraction of the either internal or external fluid volume, which can take quite a bit depending on how big our model is, what our fluid volume is, how complex the contacts are, things like that. From there, it's a separate step to mesh, right? So we create our fluid volume, make sure that everything is watertight if we're doing an internal analysis like this engine cooling analysis. And then our separate step is to mesh. The platform does it in one step. It will take our flow domain, take the abstraction shape, and mesh it at the same time. And it's a different mesher. I'll talk about the mesher on the next slide, but it is what's called a hex dominant mesh. The desktop solution is a Cartesian mesher, so it takes a lot more mesh elements to build a satisfactory mesh than the platform solution does. The other really nice thing that the platform does differently than desktop is that the platform meshes solid elements and the flow domain with different element types, and it meshes them independently, which allows them to mesh concurrently. When we're dealing with the desktop solution, we are using a Cartesian mesher, and the mesher is covering the entire domain, whether it's fluid cells, solid cells, and then it will interface at the boundary automatically. That is the proprietary technology in SolidWorks FlowSim desktop. In the platform, we can actually use different element types for different sections. So I can go ahead and do a swept mesh on my solids. I can use a tetrahedral mesh on my solids, and then I can use the hex dominant mesh on my fluid domain, which is really, really nice. From here, once we have our basic mesh, we can do the standard local refinement, right? If I need to refine on a surface or refine at a boundary, we can do that. We can use our mesh analysis tools, go from there. So the process or the principles are the same. The process is just a little bit more automatic on the platform. The other nice thing is step 4, the job execution, right? One of the other advantages of the 3D Experience platform is the ability for cloud solutions. So I can go ahead and submit my job up to the cloud and allow my computer to not work as hard, right? I can do other things on my computer while this solution is chugging along on the cloud servers. On SolidWorks Desktop, once you submit your job for solution, it's up to your computer to calculate that solution. So that means you need to have a processor that can handle it. You need to have enough RAM to actually physically build the mesh. We need to, basically wait for our computer or the designated simulation computer to chug along on that analysis and get us to a solution. So if we're dealing with really, really large assemblies or meshes with, several millions of elements, the cloud solution really shines through because it allows us to calculate those jobs a lot faster than we would if we were solving on local hardware. The post-processing is exactly the same, right? We can, depending on what we're looking for, we can either take a look at pressure drop, make sure we're maintaining a specific temperature on our engine so things aren't overheating. If we're looking for inefficient cooling zones, we can go ahead and post-process exactly how we would normally on desktop. The results post-processing is exactly the same. We can go ahead and modify our cooling channel just like we would on desktop, right? Maybe we're changing the diameter of the cooling channel. Maybe we're changing the initial conditions of the coolant. Maybe it's coming in a little colder. We want to see what that temperature drop is going to be. Maybe we're changing the material of the coolant, right? Maybe we're going from water to something a little bit more exotic, like a refrigerant or something like that. We can go ahead and run that. Then we can run our automatic trade-off studies, right? So these last two steps, we can do exactly in desktop as well, right? We can go ahead, modify our geometry, modify our design, modify our inputs, change whatever we're looking for, and we can run those what-if type analysis. What if the coolant came in with a higher flow rate? What if the coolant came in at a colder temperature? What if we change the coolant? What if our coolant diameter is a little bit bigger? We can pull a little bit more heat out of the system. We can get all of those questions answered very, very quickly. And then we ultimately come to our outputs, right? We get either the optimal design of the coolant channel if we have to do a little bit of rework. We could take a look at the engine operating temperatures just so we know what they are, right? Depending on what we're looking for, whether it be flow rates, pressure drop, we ultimately arrive at the answer that we are looking for. The other really nice thing about the platform is this automatic feedback loop right in the middle of our screen here, right? If we do need to make changes, so maybe our step 6, the results the first time are not what we were looking for. We can go ahead, make our changes either into the geometry itself or to the simulation, and we can engage that feedback loop, right? We can go ahead, automatically update our mesh, automatically update our model setup. We can go ahead and update our material properties, calibrate our material model, do everything we need to do, and we get that loop it's a lot tighter than it would be if we were either outsourcing this to another program, using SolidWorks Desktop. We can go ahead, nothing changes in the simulation setup that we don't want changed. So we can go ahead and just flip that loop and go faster and faster and faster, and we ultimately arrive at our answer faster than we would using either an outsourced program or SolidWorks Desktop. The other really nice thing about the platform is this guided scenario creation. So one of the things that I don't love about SolidWorks Desktop, there's a lot of things I do love about the desktop program, is that it's a little bit intimidating to get into if you have no knowledge of flow simulation previously, right? In this case, our scenario is we have 2 pipes coming into a junction, right? We've got one pipe that's a little bit bigger, that's going to be a little bit colder, right? We've got the same velocity, but the temperature is about 300 K. This second pipe is a little bit smaller, same inlet velocity, and it's a little bit hotter. So we're going to check out how these 2 fluids mix and come out of this exit pipe. The assistant in SolidWorks or in Fluid Dynamics Engineer, and this is not unique to the flow solution on the platform, there's an assistant as well for the plastics injection solution and the structural scenario solution. But the assistant panel is really, really nice. We got a preview of it in the video that I showed at the beginning of this PowerPoint, but what it really does is walks us through step by step, and it won't let us proceed until we have the step defined. So the first thing we need to do is specify our model, right? We need to specify what we're actually including in the simulation. We need to specify our flow domain. We need to specify our lids. In this case, we can see one lid here. There's lids on both of these outlets as well. We need to specify our physics, whether it's a steady state step, whether it's time dependency, and then we need to specify our dependencies, right? Whether our velocity changes in time, whether our pressure changes in time, whatever we would do, we can go ahead and get a step-by-step walkthrough for each of these. We can turn on physics like laminar and turbulent flow. We can turn on things like gravity. We have full control over everything that we create in this scenario. The initial conditions is dependent on whether or not we have a transient step, right? If we have a time-dependent step, we can go ahead and update our initial conditions so we know kind of what's going on at the beginning of our solution and watch the simulation update in time that way. The boundaries, same thing, right? We need velocity boundaries, pressure boundaries, whatever we were looking for. That's basically our problem setup or our boundary conditions. Contacts, if we are dealing with thermal contacts, right? If we're dealing with heat transfer, we can go ahead and specify that. Our zones, if we have things like porous media, we can go ahead and specify any special zones in our model. If we have rotating regions, if we have fans, if we have anything like that, that would be under the zones category. Then we would go ahead and mesh. Obviously, can't have an analysis run without having a mesh built. Then we can go ahead and hit simulate, which is basically the run button in SolidWorks Flow, right? We can go ahead and run, and then we can go ahead and post-process and take a look at all of the really cool pictures. We can also define multiple scenario definitions for the same mesh. One of the really nice things about the desktop or the platform solution, I should say, is the ability to reuse the mesh. The mesh gets saved as its own physical object on the platform. So I can go ahead and pull that mesh into a brand new simulation and go from there. So I can go ahead and say revision A, maybe I want my velocity to be 5 meters per second. Revision B, I want my velocity to be 15 meters per second. I can go ahead and do that, set up those two revisions, and use the same mesh in both studies because nothing changed other than my boundary conditions. And I can go ahead and compare study A with study B, or revision A with revision B very, very quickly. We also have advanced solver controls that are not available in desktop. These are for more of the power users or the people that are around STFD every day. Most of the default solver controls work just fine on the platform, but they did open the door and allow us to take a look at all of these advanced solver controls if we wanted to. The automatic interface creation for CHT, which is conjugate heat transfer, is really, really nice. The desktop solution does this as well. It creates the interfaces between solid and fluid for us. So we can go ahead and take a look at things like convection, conduction between solids, radiation, if we wanted to include the effects of radiation in our analysis. Everything like that is done automatically in the background thanks to this assistant. We have a ton of different fluid and thermal boundary conditions, right? Pressure conditions, flow rate conditions, fans, rotating regions, pretty much everything that we have in desktop is available on the platform as well. And then we have model validation before the solvers actually run. So rather than on the desktop solution, if we miss a step, right, if we forgot a boundary condition or we forgot to define something, we get halfway through the run and then we would get an error or the solver would terminate and then we've wasted an hour or however long we were waiting for that solution. On the platform, it actually will run through a model pre-check. So it'll go ahead and run through, make sure all the boundary conditions make sense, make sure the mesh is built correctly, make sure everything is good to go before it actually kicks off the run. So if we forgot a step or we missed a step somewhere, it will give us a heads up before we actually spend time waiting for this to solve. And then rather than goals in desktop flow simulation, right, the output requests are kind of the same thing. With desktop flow, we always recommend setting a goal for whatever you want to measure from the simulation, whether it be pressure drop or temperatures of specific components or flow rates, whatever it might be. The platform solution, we have output requests to do the exact same thing. So there are default output requests that are built into every simulation, like temperature, pressure drop, flow rate, things like that. But if we wanted to get really specific and say, hey, I'm specifically looking for this, we would go ahead and specify our output requests to satisfy that information. And that would be done under the results section here. We can go ahead and create an output request and go from there. The meshing is one of the really, really cool parts of the platform solution. The hex dominant mesh is probably my favorite upgrade or comparison to desktop for a couple of reasons. One, we need minimal user input. It is a robust mesher for complex geometries, and it's actually a body-fitted mesher. So what that means is it actually takes a look at the fluid volume, the abstract fluid volume, and it will build the mesh on the surfaces first, right? So in this case, if we take a look at this propeller blade design, it builds the mesh around the surface first, and then it will fill the volume afterwards, versus the desktop mesher is a Cartesian mesher where it builds the mesh in XYZ space and then tries to try and fill with really, really tiny mesh elements around the boundary layers or around the inlets and outlets, wherever we specify for the local mesh controls. The body fitted mesher, the hex dominant mesher on the platform, works from the surfaces outward. So we capture all of those surface layer interactions first, and then we fill the volume. We can kind of see in this gap down here, we fill the volume after the fact, which is really nice. The other thing about the meshing in the platform version is we have the ability to work with multiple different element types, right? We can see the hex type right here, but we also have tetrahedrals, pyramids, prisms, and it actually meshes the solid and fluid sections independently. So we can mesh the fluid volume very quickly. Oops. We get body fitted, so it's a lot higher accuracy. It interfaces with multiple mesh types. So the solid physics and the fluid physics interact with each other automatically. And it is a reduced cell count versus a tetrahedral mesh or a Cartesian mesh alone. It is more accurate with less mesh elements, which translates directly to faster solution times. So we get a time saving in terms of both mesh and solution time. It's good quality with what we call low skewness. So the elements don't come out crooked, right? They come out the way they should. And then we can go ahead and just take a look at an example, right? In this case, this is an electronics analysis. It's got a bunch of heat sinks sitting under those two chips, which we'll see in a second. This is just our temperature distribution. But in this analysis, we're just taking a look at this video. We're just taking a look really at the mesh. So in this case, we're going to go ahead and take a look at what's called our mesh part manager. We can see just how many different mesh bodies are actually fit into this analysis. The first one is our fluid domain, which is our hex mesh. So we can go ahead and turn that on so we can actually see it. That's our fluid domain number 1, which we can see is kind of our inlet and outlet, our cooling analysis. We can go ahead and see that it takes the shape of that abstract. And once we do a section cut here, we'll be able to see it a little bit clearer. So we turned off all of our geometry. We can see it wraps around all those capacitors. We're going to go ahead and do a little section of our mesh so we can go ahead and see just what it did. We can see it's automatically captured our boundary layers around all those different capacitors and kind of filled the volume after the fact. We can go ahead and use our mesh part manager to take a look at hex mesh number 2, which is our second fluid domain. So in this case, we've actually got 2 flow domains in this analysis. We can take a look at our solid mesh, which is the capacitors themselves. So we're going to do a mesh cut again. We can see how these bodies interface with each other. And then we can go ahead and turn on our sweep mesh, which is our board and our chips. So we can see just how nice we can create these different mesh domains without having to try and build one kind of global mesh or local mesh that will encompass all of these different things, right? We've got multiple physics going on. We've got different flow domains. We've got solid physics. We've got conduction. We've got convection. We might have radiation depending on what we set up in this analysis. So we've got a ton of information, but we can break it down almost component by component or domain by domain and grab our mesh very, very quickly, especially with simple geometry like those chips in that board. We can just go ahead and sweep a mesh right through that versus having to create either a Cartesian mesh, a tetrahedral mesh. However we want to build that mesh, we can just go ahead and say, okay, I'm going to sweep the mesh through with 5 layers or 6 layers, whatever we think is necessary to capture those physics, and go from there. It's much, much easier to solve when our elements line up correctly like that. Here is where we do a direct comparison between the platform solution and the desktop solution. So don't worry, guys, desktop flow simulation is not going anywhere. It's still a very competitive product. It is great at what it does. The desktop just expands the possibilities, right? Both Fluid Dynamics Engineer, which is our cloud solution, and SolidWorks Desktop can handle multiple different problem sets, right? It can handle transient problems, steady state problems, which is our most common use case, heat conduction, convection, radiation. Both, as of a couple months ago, now have electronics cooling scenarios, right? So the desktop solution has the electronics cooling module for things like heat pipes, thermal sinks, more advanced PCB board design. The desktop or the cloud solution also has those capabilities that were added a couple months ago. We can handle both laminar and turbulent flow. We can do mixing. We can do free surface. We can do everything that we can do on desktop. So desktop is not going anywhere. What sets Fluid Dynamics Engineer apart is the mesh and the cloud solution, right? Desktop, like I've been alluding to, is a Cartesian mesher. So it has to build the mesh in XYZ space, and it can result in excessive mesh elements if we need to make sure that we're capturing a boundary layer or we're capturing conduction through a very thin wafer or something like that. The platform option is much more efficient because it's a body fitted mesh, so we get more accurate solutions with less element count. So that in and of itself is a time saving. But also, the desktop is limited by your physical hardware, right? If we only have a certain amount of RAM or we only have a processor that can go so fast, that's where we're hitting a bottleneck, right? That's where our solution gets stuck until we can chug through that bottleneck and eventually get to the answer. Especially if we have a mesh that is several 100,000 elements or a million or 5 million, 10 million elements, we can only go so far with current desktop hardware. With the cloud computing option on the 3D Experience platform, that is not an issue, right? We can go up to 50, 60, 70 million elements, no problem, depending on what our application is, right? We can just go ahead, grab as many cores on the cloud as we need. We can go ahead and let that job run. And our results, one, are automatically stored on the cloud. So we can go ahead and access them from anywhere, because a result set that large is going to be a pain to kind of manage, right? Especially if we're dealing with desktop and we have to make sure that it's up to date, make sure it's shared with the stakeholders that it needs to be shared with. With the 3D Experience platform, it's a non-issue because the results are written directly into your collaborative space, and we can just go ahead and give access to whoever needs them. In summary, right, the value add of the desktop or the cloud solution as compared to desktop is quite a few different things, right? We can create really complex simulations, leverage our cloud computing power. We don't need the expensive hardware in the first place, especially with today's computer parts market. It's near impossible to get any replacement parts or any new parts because there's just a bottleneck there in the market that we can't control. But no expensive hardware needed. You can use somebody else's hardware to do your calculations. We can communicate ideas, design changes, and updates very easily, all in one location, right? If I'm working on a flow simulation and I've got results that I think are valid, I can simply just send an email or send a message and say, hey, go check them out. And I don't have to send them to you. I don't have to manage them on the server. I don't have to do anything like that. I can just let you know they're ready, and you can go ahead and take a look at them. We can bring them in to our browser. We can go ahead and interrogate them directly in the browser. We can download them for full access, full post-processing, animations, cut plots, flow trajectories, anything that we can think of that we can do in desktop, we can do on the platform. We can manage our simulation and all of our other CAD data directly on the cloud, right? So as soon as we upload from SolidWorks using the desktop connector, that data is now in the cloud. So I can go ahead, I can pull it down, make a change in SolidWorks, update a new revision, or just change the current revision, throw it back up in the cloud, move over to my flow simulation application, pull down the new revision or pull down update the current revision, pull down those geometry changes somehow, remesh, rerun, and get our new results. So our design cycle becomes that much faster. It's really, really nice to grab all of that information directly from the source, directly from the same spot. That's all I have for you guys today. I will leave the Q&A open. I'll leave the chat open for a couple minutes just in case you guys do have any questions. But other than that, guys, have a wonderful afternoon. Have a great rest of the week, and I'll talk to you guys soon.